Welcome to the second lecture in this series, and in particular, this will be the second lecture in which I will be trying to convey the intuitive idea of an integral. You've already seen how area motivates the idea of an integral, but we've also seen how an integral can represent all sorts of other things as well. In the first video, we saw examples where an integral represented distance, mass, probability, volume, and so forth. And what all of those things had in common was that in each case, we could break apart the thing we were interested in, the area, the mass, the probability, whatever, into infinitesimal bits of the form f of x dx. And we would have infinitely many of these infinitesimals. And we broke the entirety up into things like this so that we would have some function f which is effectively constant over some infinitesimal distance or some infinitesimal bit of time or whatever it might be. And even though this function f varies globally, on a local scale, we could say that it is effectively constant. And then once we had an expression for a typical bit of area or mass or volume or whatever it was, we would then integrate, meaning we add all of the individual bits, all the infinitely many infinitesimals up as x runs from some value a to some value b. And in that way, after first breaking up the whole into infinitesimals, we reintegrate it into a whole again like this. And now on our second pass through this topic, the best way to wrap up all that we did in the first video is to think of the result as a weighted sum of infinitesimals. This is a vital perspective on integrals, so I want to dwell on this for a little while. When we have some function f and we want to integrate it over some interval a to b, forget about the graph of f. Don't worry about that. Just concentrate on the real line, the interval we're going to integrate f over. The idea is we're going to take that interval, our domain of integration, and break it up, subdivide it into infinitely many tiny pieces, each of which is infinitesimally small. There are, of course, infinitely many real numbers in the interval AB, and we want to think of there being one of these little infinitesimal subintervals for each one of those real numbers. So if I take any old value of x in that interval, I can imagine an infinitesimal subinterval containing that real number x, and we'll call the infinitesimal length of that subinterval dx. And remember, there are supposed to be infinitely many of these, and they are infinitesimally small. Obviously, I cannot draw infinitely many of them, and I can only draw them so small. In fact, if my count is correct, there are actually only 24 subintervals in my drawing. But what you have to imagine in your mind's eye are not 24 of them, or 2400 of them, or 24 million of them, or 24 trillion of them. You have to imagine infinitely many of them, more than any possible number you could state. And therefore, the length is going to be smaller, this infinitesimal length, smaller than any possible positive real number. And yet still not zero. This is the act of imagination that drives integral calculus. But anyway, at each real number in that interval, we have some infinitesimal subinterval surrounding that real number. Take this real number, there's some infinitesimal bit surrounding it. Take this one, there's some little infinitesimal neighborhood surrounding it. Those little guys, all those little dx's, those are the infinitesimals of which we will take a weighted sum. Now, what do I mean by that? Well, at each real number x in the interval, we'll take dx, the length of the infinitesimal neighborhood that surrounds x, and we attach a weight to it. In other words, we're going to multiply that individual dx by something. And that weight is going to be f of x, namely the value of the function we are integrating at that particular point. So f of x dx represents, in this very general setting, a weighted infinitesimal, because we took this infinitesimal bit and we attached this real weight to it, f of x. But of course, we have infinitely many of these things, one for every value of x in that interval from a to b. So we don't just want one of them. We don't just want a single weighted infinitesimal. We want a weighted sum of all the infinitesimals. So for each infinitesimal in that interval, we multiply it by the value of the function at whatever point we're at, and then we add all of those weighted infinitesimals up, and that is our weighted sum. That is our integral. That idea, as I said before, is crucial for understanding what an integral is in a deep sense. Some of you may be thinking, that's too weird for me. I prefer to just go on thinking of it as the area under a curve. Well, that will only get you so far. This notion of an integral as a weighted sum of infinitesimals, however, will carry you all the way through calculus. I don't just mean in this course, but I mean when you get to multivariable calculus and you do double integrals and triple integrals, when you integrate over a curve or integrate over a surface or integrate over any damn thing. You can always think of any kind of integral as a weighted sum of infinitesimals, whereas this business about the area under a curve really only works in this one very particular setting of a freshman calculus class where you're just dealing with very simple functions defined on the real number line. But calculus goes much, much, much deeper than that. So this is the idea that will carry you through all integrals you meet in the future. I sometimes like to imagine a mythological creature called the integration demon. We need a demon, or I suppose he could be an angel, but for whatever reason I always think of him as a demon, to do our summing because mere mortals can only add up finitely many things. But an integral is an infinite sum, and an infinite sum at that of infinitesimals, which we have a hard time getting our heads around, except as helpful abstractions, but which the integration demon, who understands these things very well, can handle with ease. So the idea is that if we instruct the demon to integrate some function over some interval, he flies down to the scene, visits every point in that interval, and at each one, he says, aha, here's the infinitesimal dx. Now I need to attach a weight to it. What do I attach to it? Well, whatever f's value is there. So I attach f of x to it. And he has this expression, f of x dx, this infinitesimal, and he records it in his little book. And as he goes, then he flies to another real number in there, finds the f of x dx there, and then he flies to some other point. He can do it in whatever order he wants. Gets the f of x dx there. And each time he records those weighted infinitesimals in his little book. And at the end of the day, when he has visited all the infinitely many points in there, he uses his diabolical skills to add all the things in his book up, which is, of course, to integrate from a to b. And while that might seem like a silly way of thinking about it, I think you'll find that in future courses especially, it can help a lot. I mean, we're not going to be doing multiple integrals or anything like that in here, but just to show you what I mean, in a later course, you will do things like integrate over some region of the plane. So here's the xy plane, and here's this region R. And we could have some kind of a function, say f of xy. Now you may never have seen anything like this before, a function of two variables. You have to put two inputs into the function to get one thing out. And the idea is that I could take any point in the plane, take its x and y coordinates, stick it into the function, and I get some number out. Maybe the value of the function here is 32, and maybe the value of the function here is 212, and maybe the value of the function here is 0, whatever. But it is possible to make sense of the idea of integrating this function over this two-dimensional region. The idea is we disintegrate the region, but now instead of little infinitesimal bits along a one-dimensional line, they are little two-dimensional infinitesimal bits, like little infinitesimal squares, you might imagine, that are infinitesimal in both dimensions. Well, what would it mean to integrate this function over this region? If you have in your mind this idea of an integral as a weighted sum of infinitesimals, it's easy to understand. To integrate f over this region means to send our friendly, or maybe not so friendly, demon down to the region where he goes to every individual spot, surrounds it with an infinitesimal square, which has an infinitesimal area that we call dA. And of course, he takes that infinitesimal bit of area, he attaches a weight to it, namely the value of this function at that point. So that's going to be something like f of xy, whatever the value of function is at that point. If that point, say, is xy in the plane, and then he's going to add them all up. And you might say, yeah, but what are the boundaries of integration? Isn't that weird? Yes, it is weird. And we're not going to talk about that in this class. Very briefly, though, what we actually do is write two of these guys to indicate that it is a so-called double integral, an integral over a region in two-dimensional space, and then we just write R underneath, telling us we're doing the integral over all points in that region R. Anyway, that's more complicated than anything we'll be doing in this class, but it is in your future, for most of you anyway, and if you understand the idea of an integral as a weighted sum of infinitesimals, it's very easy to understand intuitively. whereas trying to understand this in terms of area under a curve doesn't work so well. There is a way to do it, at least area under a surface in three-dimensional space, but even that breaks down, because what if I have a function of 5 variables instead of 2? Then the region of integration would be some chunk of 5-dimensional space, which we can't even draw. And thinking of the area under, it's not a curve, it's not a surface, it's some kind of complicated hypersurface, not helpful at all. Totally defeats our geometrical intuition. But thinking of a weighted sum of infinitesimals, not so bad. Whatever the region looks like in 5-dimensional space, we don't even have to worry about that. We just know that we visit every point in it. We get some little bit of infinitesimal bit of hypervolume, as it would be, attach the value of the function to it, and add them up. And that's the intuitive idea. Okay, but enough of multivariable calculus. In the first video, I was careful to discuss only functions that were strictly positive, that had positive values over the interval that we were integrating over. So something like this was just fine for what we were talking about last time. And that's what allowed us to think of our integral, our weighted sum of infinitesimals, as an area, because each dx gave us the infinitesimal width of a rectangle, and the value of the function gave us the corresponding height, so that f of x dx was the area of that infinitesimal rectangle. And when we summed them all up, we got the entire area under the curve and over that integral. But as you know, not all functions are strictly positive. And we could certainly talk about integrating a function whose values are sometimes positive and sometimes negative over an interval. Maybe one whose graph looks like this. The idea of integrating such a function over an interval would have felt a little awkward in the first video, but now that you understand the idea of an integral as a weighted sum of infinitesimals, the intuitive idea of what it would mean to integrate f over ab should be pretty clear. Nothing has changed, really, especially if you think of this fellow, the integration demon. Imagine commissioning him to go down to this interval, ab, and compute this integral. What does he do? Well, he goes to all the various points. Aha, here's one. He takes his dx, he weights it with the value of f there, he gets some positive infinitesimal, f of x dx, and he writes that down in his little book. And then he goes to another point and does the same thing. Aha, there's dx. He multiplies it by the value of f there. It's still a positive number. So he gets some different f of x dx. Well, that goes in the column below it. And he does that again and again and again and again, everywhere at every point throughout this interval. The only thing to bear in mind is that sometimes, namely whenever he is in this region, or actually in this region as well, when he takes his dx and then says, now it's time to attach the weight. Here I am at x. What's the value of f there? Bop, he gets a negative value, so that his f of x dx at that one point would be a negative infinitesimal. Well, that's fine. That just means that he has a negative infinitesimal in his list, so that when he adds them all up, if all the positive infinitesimals are summing up to something positive, this just eats away at the running total if it's a negative infinitesimal. It's just like an account book with credits and debits. And at the end of the day, after he's done all his summing up, the total might be positive or it might be negative. Nothing mysterious about it. The integration demon can work with positives and negatives as well as we can, of course. Let me give you a quick example that I think will make the idea clear. Suppose we want to evaluate this integral, the integral of sine x, as x runs from 0 to 2 pi. Now you might say, hey, wait a second, we haven't talked about how to evaluate these things yet. You said we'd need the fundamental theorem of calculus for that. And in general, that's true. But in this case, the symmetry of this function will allow us to determine the value of this integral very easily. This is easiest to see if we think of the graph of sine x, which of course looks something like this. Well, what does this integral ask us to do? It asks us to shatter this interval, 0 to 2 pi, into infinitely many infinitesimal bits, and then form a weighted sum of those infinitesimals by taking each point in there, taking that little dx, multiplying by the value of the function there, and getting a weighted infinitesimal of the form sine x dx. Sometimes the weighted infinitesimal will be positive, sometimes it will be negative, but we will sum them all up. Well, I think you can see what's going to happen because, for example, our integration demon is going to have to visit this point, and he's going to get a positive infinitesimal right there because the value of the function is positive there. But there's a point exactly on the other side where he's going to get the same value but negative. So whatever his little f of x dx is here, that positive infinitesimal, it's going to be balanced in his ledger by this f of x dx right here because the value of f is going to be negative right there. And the absolute value of of those two f's are going to be the same, so they will cancel each other out in the grand sum. And I hope you can see that for every point between 0 and pi, there's going to be the corresponding one between pi and 2 pi, where the f of x dx we get here is going to be balanced by the f of x dx we get here, because in this case it'll be negative. It'll be equal but opposite right there. So what's going to happen when he adds up all of his f of x dx's? And f of x, of course, in this case is sine x. So what happens when he adds up all those sine x dx's? Well, for every positive one he gets, it's going to cancel with a negative one, which means at the end of the day, all of this is going to wash out to 0. Congratulations, you've just evaluated your first integral. Most of them won't work out so simply, but if you have this idea of an integral as a weighted sum of infinitesimals, you should be able to see why this is 0 without doing any actual calculations. Similarly, you should be able to see that if we take sine of x and integrate it from pi to 2 pi, so just this part of the real line, everywhere we go, the sine x is going to be negative for every x in there. So every one of those sine x dx's is going to be a negative infinitesimal. So our integration demon will just be adding up negative infinitesimals as we go, which means he'll get the sum of negative, 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 negative. The whole thing is clearly going to be a negative number. Never mind what it's going to be, but it will certainly be negative. But let's put this specific example of sine x aside for now and think about how we can interpret the integral of a function over some interval where the value is negative throughout. Can we connect it to area the way we could when the function was positive? We can, and the idea is easy enough to see. You may see it already. If we take any old real number x, somewhere in that interval, take an infinitesimal neighborhood of it, of length dx, and to that dx we attach the weight f of x, the value of the function f at this real number x, well, what do we get? Well, happily, we get something which I could see graphically in terms of this infinitesimal rectangle. Now, f of x is not the height of that rectangle, because f of x is a negative number. It's got the right magnitude, but it's got the wrong sign. That means the height of that little infinitesimal rectangle is negative f of x. If f of x is negative 2, then the height of that rectangle, of course, is 2. So it'd be negative, negative 2. We have to negate the negative value of the function to get a positive, which of course any distance is going to be positive. So that means that the area of this typical infinitesimal rectangle at x is not f of x dx. It's minus f of x dx, like so, which means that if we go back to the question of what does it mean to integrate f from a to b, to take our f of x dx and add those guys up as x runs from a to b, we are adding up f of x dx's. So we're adding up these things which are the negatives of the areas of all of those rectangles. Well, if we add up all of those rectangles' areas, except that we have a negative attached to each one, what we end up with here is not the area under the curve, or above the curve in this case, but rather the negative of the area above the curve. So if we happen to know, say, that this area is, let's say, 8, then when we integrate our function f from a to b right here, what will we get? Not 8, we will get negative 8. And this sort of thing is nice because it gives us a way to connect integrals to areas and graphs, even when the graph dips under the horizontal axis. So for example, let's go back to this picture I originally drew over here. For the sake of argument, let's say that this area is, let's say, 15 square units, and that this area is 22 square units, and that this area is 3. And this area is 2. And finally, this area is 3. If we're given all that, then what can we say about the integral of that function f from a to b? Well, this is very easy to see if we think of this as a weighted sum of infinitesimals. We're going to start at a and go to b and add, although those are subtractions really, because the value of the function is negative. Add, subtract, subtract, add. And what are we going to end up with? Well, imagine breaking the task. Imagine the integration demon breaking up his task into 1, 2, 3, 4, 5 little bits. First, we get the weighted sum of all the infinitesimals from a to this point right here. All the values of x in there. Well, what's that going to be? That part is just going to be the area under the curve. So that's going to be 15. But we're not done. He can rest and have a lunch break here, but then he's got to go get all those weighted sums and add here. Well, as he goes from here to here, adding up all those weighted infinitesimals, overall what he's doing is getting minus 22 over that particular stretch of the real number line. So he's going to have to subtract off at the end of the day 22. Well, you can see what's going to happen. Then he's going to end up adding 3 and subtracting 2, and then on this last little bit, adding 3. And now we have equality. This weighted sum of infinitesimals, all of them, as x runs from a to b, well, we just did it in a few different parts. First, we did it as x runs from a to whatever, giving us 15. Then as x runs from whatever to some other whatever, giving us minus 22, and so on and so forth. When we put that all together, we get, let's see, 18, 21 minus 24 is minus 3, if my arithmetic is correct. So even though this function is sometimes positive and sometimes negative, we can still interpret its integral from a to b in terms of area. This minus 3, that's telling us that there's 3 units of area more on the negative side than there are on the positive side. And that's that. Let's think about a physical example next. An example where we're integrating a function that is sometimes positive and sometimes negative. Last time we talked about taking a speed function, say s of t, which is necessarily a positive function because speed can only be positive, or 0, I guess, but not negative. Like distance, speed is always a positive quantity. And we saw how if we integrate that over some interval of time, well, at any given value of t, the speed is effectively constant. So we have a constant speed times the time in which it's moving. Well, constant speed times time is distance traveled. So s of t dt is the distance traveled in an instant. And then, of course, we add up those distances traveled for all the instants between time A and time B. And so we ended up with the distance traveled between time equals A and time equals B. So far, so simple. But if instead of looking at speed, we were looking at an object's velocity along some particular dimension, let's call that v of t, well, now we're in a slightly different situation because velocity is speed and direction. Positive if we're moving in the positive direction, negative if we're moving in the negative direction. So if we have some stretch of highway and a particular spot marked on that highway, or a pebble or whatever you like, let's say we have a bug flying around above the highway there. And let's say we do not care about his height at any given moment. We only want to know, is he to the right of the pebble? And if so, how far? Or is he to the left of the pebble? And if so, how far? And how fast is it moving? And is it moving to the right or to the left? And again, we don't care anything about the vertical component of his motion, only the horizontal. So we're thinking of this velocity function, v of t, as registering not just how fast, because it's not just speed, but it's velocity. So if he's moving to the right, if he's right here and he's headed up this direction, then his motion, his horizontal motion, is in this direction, meaning he'll have a positive velocity there. But once he's whipped around that corner and he's here, now he's moving, at least the horizontal component of his motion, to the left. So this function, which measures the horizontal component of his velocity, will be negative. And maybe sometimes he's moving really rapidly, and sometimes he's moving really slowly, probably moving rapidly on these long stretches here, and more slowly when he's reversing his direction. But whatever, this thing is varying. Sometimes its magnitude will be great, sometimes it will be small, sometimes its sign will be positive, sometimes it will be negative. It's definitely varying over time. But nonetheless, at any given instant, in the infinitesimal neighborhood of any moment in time, the velocity will be effectively constant. Not just in a second or a millisecond or a picosecond or whatever it would be, but in an instant, his velocity has no time to vary. So that means it's effectively constant. It might be positive or it might be negative, but it is not changing. And when we have a constant velocity, then multiplying it by the length of time in which that is constant, so some dt, some infinitesimal bit of time, again, it gives us something like the distance traveled in that instant, except because this v of t could be positive or negative, it gives us not just the distance traveled, but the direction in which it is traveling as well. If this is positive, that's the distance it moves to the right. If it's negative, it's telling us that it's moved a certain distance, whatever the magnitude of that is, but to the left. And the way we would actually describe this thing is we would say that is the horizontal displacement during the instant dt. Meaning, is the fly moving a little bit to the right or a little bit to the left? And of course, if we sum up all of those horizontal displacements, as t runs from some time a to some time b, then we get the total displacement between time equals a and time equals b. This is built up from all the individual displacements. So the positive displacements will cancel with negative ones, and we'll end up with something that is possibly positive or possibly negative or possibly zero. If, for example, we found that the integral of velocity from time a to time b was, let's say, -7, and let's say the units are feet, then what that would mean is if we're following the bug, then wherever he started, well, he ended 7 feet to the left horizontally. Maybe he rose up 100 feet, or maybe he's on the ground, who knows? But this is telling us that he would be 7 feet further to the left, even though sometimes he's going right and sometimes he's going left. Or if this turned out to be not -7, but 42 feet, that would mean that whatever zigzagging he does over this, at the end of the time interval, he's 42 feet further down the road than when he started. Or finally, if that integral turns out to be 0, that would mean that however he ends up flying around for however long we're following him, when the clock ends, he's at the same horizontal place where he began. He has been displaced neither to the right nor to the left, at least overall. At any given moment, he might have been a mile down the road this way. Who knows? But when we add up all those little displacements, he ends up in the same place he started. Okay, let's look at a different kind of example. Not a physical example, but just for fun, a kind of speculative example. A fake, but perhaps theoretically interesting psychological example. Let's say we're interested in the idea of happiness, and we can imagine some theoretical function h of t that measures some kind of notion of happiness at any given time t. In fact, strictly speaking, we would probably think of this not as measuring happiness itself, but some kind of theoretical happiness density, which might be measured in, let's call our happiness units hedons. So our happiness density would measure hedons per unit of time. As I think I mentioned in the last video, one of the sorts of things we integrate frequently are various kinds of density functions, which can be a little hard to get your head around initially, but they are the kinds of functions that we like to integrate because they have a very simple interpretation when we integrate. For example, if this is our happiness density, we can imagine at any given moment, it might have a high score, and we have a high density of happiness. In any given unit of time during which the happiness density is high, we get lots of hedons, lots of units of pleasure. At some other moment in time, t, maybe this score is close to 0. Or maybe it's even negative, in which case we get negative hedons per unit of time. We're experiencing not happiness, but sadness. Anyway, now we could bring in the philosophers and the psychologists and have them argue about who has the happiest life, given the graphs of various people's happiness density functions. For example, let's say this is one person's happiness graph. So let's call it h sub 1 of t. And a and b are just 2 times, and we'll consider the same times for all, let's say we'll look at 3 people. So this person starts out maybe fairly low, but at least positive, and over the interval of time we're looking at, gets happier and happier. Well, that's pretty nice. Even though the person started out low, things are looking better. Or we could look at person 2 over the same interval. Maybe this person's happiness graph looks like this. Let's call it h2 of t. This person starts out pretty high and gets really high, maybe in more senses than one, and then crashes after the drugs have worn off or after some bad thing happens, whatever. So we end up with very high happiness for a while, but then followed by a plunge into quite the opposite. Or finally, maybe we have someone whose graph looks like this, h3 of t. Same level of happiness throughout. Never as high as either of our first two, but never as low either. So we can ask our assembled philosophers and psychologists, who is the happiest person, at least over this interval from time A to time B? Well, there are plenty of ways you could define that notion, and that's what they're going to argue about. But at least one way you could think of it is imagining happiness as an integral. After all, if h of t is our happiness density measured in hedons over units of time, then h of t dt suddenly now has the right units, because this would be hedons per unit of time, and then we're multiplying by unit of time. So the units on something like this would be just plain old hedons. Each h of t dt would be measured in hedons. And then if we add them all up, well, we would get the total number of hedons experienced by a person between A and B. And this could be a net positive or negative or zero. And of course, we could interpret this in terms of area under the graph. So one way to argue the point would be, well, look, who's the happiest over this stretch of time? Well, we need to compute that area right there. That's our integral. That's going to give us the area under the curve is the total happiness of person 1. It's the total net change in hedons. Meanwhile, person 2 picks up a lot of area at first, but then loses a lot of it too. So who knows? By eyeballing it, I can't tell. Maybe if we subtracted that off of this, we'd be left with something like that. I think the integral of this function from a to b would actually be greater than the integral of this function from a to b. So that would be one way to argue that person 1 is happier than person 2, despite the fact that person 2 had this great moment of exaltation, which person 1 never had. And what about person 3? Well, the area under his or her graph looks like that, which, you know, is probably pretty close. It might actually be slightly greater than that one. So maybe you could argue that this person is the happiest, even without this variety of highs and lows, or in this case, at least a sense of increasing happiness. This might be your Stoic philosopher or something like that. But anyway, as I said, this is just a silly speculative example, but it gives you some sense of how integrals can actually provide some language for talking about such things. But now, let's return to mathematics proper, because there's one last notion related to integration that fits into this lecture well, and it's something that I notice students don't learn as well as they should in a pre-calculus class. And this is the idea of even and odd functions. Most people first encounter this idea when studying trigonometry, because just about all of the trigonometric functions are either even or odd. So I'm guessing you've met this before, but I want to review the basic ideas and then talk about how they link up to some properties of integrals. So let's start with the definition. F is said to be an even function if f of negative x is equal to f of x for all the x in f's domain. So what does this mean less formally? It means that if you take any x in f's domain and look at its negative x, the function sends both of those values to the exact same place. F of x is going to be the same thing as f of minus x. So wherever f sends 86, it's also going to send minus 86 to the same value. Whatever f of negative 113 is, well, f of positive 113 would be the exact same thing. Some specific examples of even functions. The squaring function, f of x is x squared. Is this an even function? Certainly, because f of minus x is the square of minus x, and of course minus x times minus x gives us just x squared, since the negatives cancel, but x squared is f of x. So f of minus x is the same thing as f of x for all x. The square of minus 3 is the same as the square of 3. The square of 17 is the same as the square of minus 17. So the squaring function is a classic example of an even function. G of x equals x to the fourth power is another example of an even function. Obviously, raising anything to the fourth power gives you the same thing as if you had raised its negative to the fourth power, because you get those four negatives that when you multiply them together, you end up with a positive. So 2 to the fourth is the same as negative 2 to the fourth. They're both 16, and so on and so forth. Another example of an even function is the absolute value function. Obviously, by definition, the absolute value of minus 17 is the same as the absolute value of 17. The absolute value of 39 is the same as the absolute value of minus 39. Most importantly, and this is probably where you met the notion of even functions in the first place, cosine x is an even function. That means cosine of minus x is the same as cosine x for any x. Cosine just absorbs that negative. Why is that? It is crucial that you understand why that is so, but that comes straight from the definition of cosine. What does cosine of x mean? Well, it means that if we rotate through an angle x on the unit circle right here, the first coordinate of that point is, of course, cosine x, and its second coordinate is sine x. That's how those functions are defined. But what about not cosine x, but cosine of minus x? What is that? Where does that live? on the unit circle? Well, the minus just means that we rotate the opposite direction, still through angle x, but clockwise now. And we get to that point, and its coordinates are going to be cosine minus x, sine minus x. And what can we say about the first coordinate, cosine x of this point, and the first coordinate, cosine minus x of that point? Well, obviously, those points have the same first coordinate, so that means that cosine of minus x is the same thing as cosine of x, and that's for any value of x through which we rotate. So cosine x is even. Or here's another one. What about secant x? I claim secant is even. Why is that so? Well, what can we say about secant of negative x? Well, by definition, it's 1 over cosine of minus x. That's what secant means, 1 over cosine. It's a reciprocal trig function. And what do I know about cosine of minus x? Well, cosine is even, so that means cosine of minus x is cosine x. And what do I know about 1 over cosine? Well, again, by definition of secant, that's secant x. So I've shown that secant of minus x is equal to secant of x for all x. So yes, indeed, secant belongs on that list. It is an even function. Okay, so we know what even functions are, and we know some examples of even functions, but you probably also remember that even functions have a nice geometric property, which comes straight out of the definition. So let's make sure we understand why this is so. If we have the graph of some even function, f, whatever it is, it could be one of these, it could be a totally separate function, it could be any even function on the planet. The one thing we know is that if f is an even function, then f of minus x and f of x will be the same for every value of x. In other words, if I take some value of x here and it's negative over here, well, wherever f sends x, it's going to send minus x to the exact same place. So if it takes this value and sends it up here, we know that it's going to send its negative to the exact same value. If it sends this value down here, we know that it's going to send its negative to that same value. And this is going to happen for every pair of x and minus x, so that the graph of the overall function might look like this or something else, but whatever it looks like, it is going to be symmetric around the y-axis. So an even function always has a nice graph that is always going to be symmetric around the y-axis. And we can use that fact, that symmetry, or just arguing straight from the definition, to come up with an interesting fact about integrals of even functions. If f is an even function, then integrating f, when we integrate f over some symmetric interval, symmetric around the origin like that, from minus a to a, what can we say about the value of that integral? Well, think of this thing as a weighted sum of infinitesimals. And let's do our summing in 2 bits. To get from minus a to a, let's just say this is minus a and this is a, we could first add up our weighted infinitesimals between minus a and 0, and we get whatever we get. We'll get some positives here, we'll get some negatives, we get a lot of more positives there, and then we could integrate from 0 to a, and we get whatever we get there. But in fact, what we get over here is going to be exactly mirroring what we got over on the negative side. For every weighted infinitesimal we have on one side, we get its exact image on the opposite side, whether it's positive like those or negative like those. So overall, in this sum, everything appears twice. So one thing we could say about this integral is we could accomplish the same thing if our poor integration demon wants to do his work a little more easily by just integrating from 0 to a and doubling the result. As we'll see later in the course, this often turns out to be a useful property because when we are actually evaluating integrals, when we learn the fundamental theorem of calculus, we'll find that it's really nice when one of the boundaries of our integrals is 0. It makes evaluating the function much more simple. And if you understand the notion, again, of an integral as a weighted sum of infinitesimals, this property is completely obvious. But somewhere later down the road, you might want to integrate, say, cosine x, an even function, from maybe minus pi over 4 to pi over 4, and you'll be able to recognize, aha, this is an even function being integrated from minus a to a. That means I could just go from 0 to a, add up my weighted infinitesimals, and double the result. And that will be an easier thing to compute. For now, the main thing is just to understand where this result comes from, which means understanding what an even function is and understanding what an integral is. If you understand those two things, this should be pretty straightforward. If you don't, then you know what you need to work on. But anyway, Enough about even functions. Let's turn to their odd cousins. Start with the definition. F is said to be an odd function if, once again, f of minus x is something in particular for all x in f's domain. In this case, f doesn't send minus x and x to the same place. It sends them to negatives of one another. So if f sends 3 to 19, then it's going to send minus 3 to minus 19. If f sends 7 to 42, it's going to send minus 7 to minus 42. So opposites in the domain get sent to opposites in the range. Some examples. The cubing function. Cubing negative 2 is not the same as 2 cubed. It's the negative of 2 cubed because you get minus 8 instead of 8. And that holds for all such inputs x. G of x is x to the 5th is an odd function. Same for x to the 7th, x to the 9th, x to the 11th. That's why it's called odd. It has to do with those odd exponents. Trigonometry is dripping with odd functions. Sine is an odd function. Be sure you understand why sine is an odd function. Again, this just comes back to sine's definition. If we rotate through an angle x on the unit circle, we get to the point cosine x sine x. If we rotate the clockwise direction, so minus x, we end up with cosine minus x sine minus x. We already said this explains why cosine is an even function. But it also shows us why sine is an odd function. Because what can I say about sine x and sine minus x? Those are the y coordinates, the second coordinates of those points. And clearly, those have the same magnitude, but one is positive and one is negative. So sine of minus x is going to be the opposite of sine x. And that's going to be the same no matter what x is to begin with. Non-surprisingly, sine's reciprocal function, cosecant x, is going to be odd. I'll leave it to you to work out the details. It works exactly the same way that we showed that secant was even. But a more important function, tangent, is also odd. There are several ways to see that. Hopefully you know some of the geometric interpretations of tangent on the unit circle, and you can see it directly. Or another way to see that tangent is odd is to use a basic trig identity. What can we say about tangent of minus x? Well, by the identity I have in mind, that is sine of minus x over cosine of minus x. Everybody knows that identity, I hope. And what do we know here? Well, what is sine of minus x? Well, sine is an odd function. So sine of minus x is minus sine x. And cosine of minus x, what do I know about that? Well, cosine is an even function, so it absorbs that negative, and what we get out is cosine x. Aha, well now I've got a negative and sine over cosine. So using that same trig identity, that's minus tangent x. And so look what I have. Tangent of minus x is the same thing as minus tangent x for all x. That means tangent of x is indeed an odd function, as I claimed. Okay, so now we know what odd functions are, and we've seen some examples of odd functions. You should also remember that odd functions have a nice geometric property that comes straight from the definition. Again, you should understand why it has that property. If you know the definition, then it's obvious. Let's say we have some odd function and we consider its graph. Well, whatever that function is, we know that if we look at some value of x and its opposite, negative x, then f, wherever it sends x, it's going to send negative x to the exact opposite place. Similarly, if it sends this value of x, who knows, up here, then it's going to send its opposite to the same place, but on the other side. If it sends this one here, well, it would have to send its opposite to the equal but opposite place like that. And so whatever its graph ends up looking like, it's going to have a particular kind of symmetry. Maybe it will look like this, but whatever it looks like, it's going to have this property, which we usually describe as being symmetric about the origin, which is a funny sort of phrase, but one way to think about that is if you take any point on the graph and fire it straight through the origin, so that it comes out the same distance on the other side, it's going to hit the graph. Or there are other ways of thinking of this. You could take the graph and reflect it first over the y-axis and then over the x-axis, and you will end up with the same thing you started with. But either from this geometric property or straight from the definition itself, we can come up with a nice property of integrals that refers to odd functions. Namely, if f is an odd function, then what happens if we integrate it from minus a to a, where a is any old real number. Well, let's think about our picture up here. If this is minus a and a, note what the symmetry does. Everywhere I evaluate in here, I take my infinitesimal and weight it with the value of the function, I'm going to get its mate over on the other side that's going to have the same length, but whereas one is negative, the other is going to be positive. So when we do the big sum at the end, when the integration demon adds up all of his weighted infinitesimals, this negative and this positive will cancel each other out. Similarly, if I get a positive over here, it's going to be balanced exactly by a negative over here. Every positive is going to be balanced by a negative. So in the grand sum, the integral, everything cancels out over the whole integral, and the value of this thing is going to be 0. There's nothing to calculate. This will be handy later on sometimes, where your classmates will be struggling to come up with a way to find an integral, but you will look and you'll say, wait a second, this is an odd function, and I'm integrating from minus a to a. Of course, that's just 0. So you will be way ahead of the game. For example, if you need to integrate x to the 19th power as x runs from minus 73 to 73, well, you can just observe, that's an odd function. We're integrating from minus something to the positive same thing. Of course, we are going to end up with 0 at the end. And if someone says, wait, why is that true? You should be able to explain what's going on in terms of this being a sum of weighted infinitesimals. All right, that's about all I've got. So we have done a lot of intuition building in these first 2 videos. In the next one, we are going to start laying the groundwork for the fundamental theorem of calculus. And then we will be off to the races. So for now, make sure you are comfortable thinking about integrals in all these different ways. You're going to need it in this course and many courses to follow. If you have that intuition, as I said in the first video, that's a third of the battle. You just need to know the computational details, which we'll learn soon enough. And of course, you have to know all the prerequisite stuff. Derivatives are going to come rushing in as soon as we get to the fundamental theorem. And of course, all your pre-calculus knowledge is vital. Pre-calculus is the language of calculus, so we need to be able to speak that fluently. All right, that's all. See you next time.